A very good afternoon, everyone present here. Today, we all have gathered here to witness the 9th lecture of our Centenary Lecture series. Today, we will get an insight about the history, fire characterization, and application of the composite material by Professor Debes Bhattacharya. Today, as a session chair, we have with us Dr. Bhattacharya, former Joint Managing Director, Usha Martin, and our beloved alumnus from the batch of 1967 as the chair of this 9th Centenary Lecture. I would request Sir to take over the session. Over to you, Sir.
Am I all right? Everybody
Yes,
can
sir,
hear me?
you're audible.
All right. Good evening, sir. Good evening, friends. I have the pleasure to introduce Professor Debes Bhattacharya, who will speak on the application, the history and the fire characterization of composites. Just a few words. We all know that the history of mankind has gone through various ages. Probably it started with fire, because all of us, we liked tandoori right from beginning. But the Stone Age, the copper, the iron, and then the alloy polymer, we have gone through all these things. As a person who has spent quite a lot of time in the metal industry, I personally believe that the incremental benefit of alloys probably are getting limited, or things like powder metallurgy, etc., getting limited. So the future of the application of material in critical application, I do not say replacement of 2 billion tons of steel or 4 billion tons of steel. I'm talking about all the critical applications won't be dependent on development of new alloys or new technologies like powder metallurgy. It will be more dependent on this composite. So for this reason, I think today's presentation by Debes will be very interesting. Debes graduated in '67, along with me, Ashok, everybody. In fact, four of us stayed in the same room in Downing Hostel. And surprisingly, four of them did their PhD, including Gora. Two are no longer with us. Debes did his master's also from BE College in '69, and then joined CMRI. And while in CMRI, he, under registration of Jadavpur, and with Dr. Chakraborty as one of his supervisor, he completed his PhD in 1978. And then after some time, he went with a fellowship to probably Australia, and then moved in the faculty in New Zealand. I believe, with my limited knowledge, whenever I have met him in his son's marriage, etc., that he has kept himself dedicated to the development and application and properties of composites. Our knowledge of composites are limited to concrete, where we know that there is a bonding matrix like cement, and you have additional materials like sand, aggregate, and reinforcement steel, which is probably a little forcible intrusion. The purpose has always been to achieve, to keep the properties or identities of the individual participants in the matrix, but achieve specifically designed properties. And things have really moved in a significant way. Debes, rather now I should call him Professor Debes, because his contribution, and apart from his academic excellence, his contribution can be measured, recognized, appreciated, whatever we call, by the fact that he has produced 80 PhD students and over 500 technical papers in international journals and books, etc. And I would like to mention one thing. New Zealand is a small country. India produces probably 5 New Zealand every year. So the students, PhD students, he has sort of matured into a qualified doctorate is not all from New Zealand. I believe they are from Australia and other Asian countries. So Debes will definitely sort of have his footprints in many countries. What he has left and what these students will do in their future. Debes has been recognized in many ways. Debes is a fellow of the Royal Society of New Zealand. Debes is, I have to read out, and should I miss any points, I request all of you to read so that nobody says I have missed something which has kept his achievements incomplete. Debes is a distinguished professor in the Auckland University. He was the head of the Department of the Mechanical Engineering. He was the founder of this advanced composite material, and he was a distinguished professor there up to 2016. Mercifully to Mrs. Bhattacharya, he retired recently to reduce his loyalty to composites. He has sort of been visiting professor to countries like educational institutes and research institutes in Australia, Canada, Germany, Hong Kong, and USA. He also had come to Chennai for conducting courses at the invitation of SRM, who had also recognized him with the award of our Kalam Award for Excellence. He is I mentioned he is the fellow of the Royal Society of New Zealand, honorary doctorate by University of South Queensland, Australia. He is a DuPont Research Awardee. He is a member of the Institute of Polymer Science fellow in the Polymer Science in Germany. Debes has interest in social work, certain religious, not religious really, at the end of the day when you talk of Belumor, etc., more of social activities. He has interest in that. Debes has taken active part in lighter side, softer side of life, which is probably influenced by Amitabha and his sitar. He has taken parts in dramas and plays. And hold on, he has played in a cinema. I'm forgetting the name. He has played a role in a cinema in New Zealand. But still, our Debes Bhattacharya remains Debes Bhattacharya, not Debes Bachchan. So that's why he is very much with us today. I will invite Debes to take over and in the introduction of a friend, one should not personalize, but I would like to say that Debes knows, Ashok knows, that the four of us, Topon, Bhattacharya, me, Debes, and Bora Bhomik, of all the persons, three of them were crazy. But still, the fact that we lived so happily is because of the bonding effect of Debes. So he was, even at that time, he was probably, he believed in the concept of, improved living through sort of bonding between friends. And Debes, thank you very much to remember old days, and I would now request you to take over. Otherwise, people will think the lecture is mine, not yours. Thank you very much. I hand over.
Thank you, Purandar. Thank you very much for giving a very kind introduction, rather flattering, but I will not dwell on that. I think we'll have to start, and let me start because I'm a little concerned whether everything will go smoothly. Can you see the screen? Can you see the screen?
No, sir, it is not shared yet.
I am sharing. It showed a few minutes ago when we tried.
So can you share it once again?
Yeah, I am sharing. Share the screen. And should. Can you see now?
No, sir, not yet.
That is exactly, I can see the screen there. It is, just a minute, I will share again, start the sharing
Have
process.
you shared through WebEx?
I am sharing, it is showing that it is shared. Entire screen, okay, it is entire screen. It was, I tried only a few minutes ago. Everything was, can you see now or no?
No, sir. So while you click the share button, you can share the application and share your entire screen there.
Yeah, that's what I have done. Entire screen.
So yet it is not displayed actually.
Just a minute. I'll start from there. Yes, entire screen. Has it improved or anything? Can you see anything?
No, sir.
Can you go back to the original screen without your shared material? Original screen with the
Yes,
WebEx?
I can see my thing, and we shared exactly that way. We can't display your shared content. Make sure that you have allowed permission. So that's where the problem is. I'm the co-host, so I should have the permission. I don't need the permission.
Maybe doing the exercise once more will solve it. You can stop sharing and go back to the original screen and start sharing. But before sharing, you please try to optimize that.
Yeah, I have gone out.
Yes.
I am just starting from share and share optimize for text and images.
And
then the screen.
Yes. And then
share screen.
Most one.
Share screen.
In one. Yes.
Yeah. And then this. That is my screen.
Yes.
You cannot see that. Can you?
No, sir. Did you click share at the bottom?
Yes, I did. Exactly, we tried only a few minutes ago. So that time you could see all my slides, everything. And
Yes.
yesterday also when we tried share the entire screen, it is showing as entire screen. Just let me see whether, can you see anything?
Not yet.
I came early just to check this. That's fine. I will. Should I start from the very beginning, or I don't know?
I'm not sure whether two web-based instances are open or not.
Share, and I'm sharing that, and then optimize for text and images. It has come. What do you want to share? Screen. That's what I want to share.
and then share.
Yeah, that share is coming in gray. It is only cancel is
So
full.
there, while you get that entire screen, you will have to click that display there. Then that share will come in blue.
Where is the entire screen? There is nothing called display. I did not see that. I said share.
Yes,
And
sir. And in a small box, there your screen is coming in a miniature form, right?
screen should, and then I have to say display. Yeah.
Yes, sir. You will have to click on that miniature screen once. Then that
Screen
share
one.
will come in. That share will come in blue, and then it will share.
I did share entire screen.
Yeah, you're
And
seeing a miniature form of that screen.
miniature form is so small I can.
No,
So something like
screen-
screen one on your left.
No, I am not seeing that. It was entire screen. I am
Make it an
normally when I say share, I see my entire screen immediately, my computer screen.
So you will have to click that screen once.
I understand, but I have to see the screen, then only I can.
So make it automatically optimized. I think.
Yeah.
Not optimized for screen and images. So basically,
I actually, let me share now again.
No, this coming. It's coming.
So it's
Can you
visible now.
can you see something?
Yes, sir.
Yes,
Yeah.
sir.
Now this share
Yeah, it has
became
come.
blue rather than I have to say hide this one.
Yes,
Can you
sir.
see now?
Yes, sir.
So it's visible.
Yeah,
Can you see?
Yes,
Okay.
sir.
that's right.
Okay. Sorry about that. We have lost a few minutes. Yes, this is I'll try to give an overview because it is a huge area, history, applications, and fire characterizations, because these areas have been very close to my heart for the last few years, and our center was very much involved. I have picked up a few areas from there, and I'll try to make it as general as possible rather than going into all the analysis or things like that. So I must acknowledge there are quite a few students who are involved, and the funding, long-term funding, we got very good funding actually from Ministry of MBIE, and also from elsewhere, from other countries. And the students, as Purandar mentioned, we used to call it United Nations because we had students from about 18 different countries. Now, those who are not familiar with with geography, this is New Zealand, and often in the map it drops off after Australia. You can see that there is a small country there, and main cities: Auckland, Wellington, Christchurch, Dunedin. Auckland is the main center where about 1/3 of New Zealand live in and around Auckland. So this is one view I wanted to show, that this is every city has to have a spike. So we also have our share. And this is the view, because this city is split between two parts, North Shore and main central area. So from the bridge, you can get this kind of view in the evening and during the daytime. I wanted to show because this is the reason why we started research in the composites area, because New Zealand first in America's Cup Challenge made the boat entirely from composite materials, and they have been very, very successful in building and manufacturing boats. Not simple boats, also for very, very expensive boats. Some of them could be 100 million, 50 million, $200 million boat with all the gadgets and everything, but the material research also has been at the top class level. The first America's Cup syndicate sponsored 6 students, and two students were worked in the composites area, 2 in the fluid mechanics area, and 2 in some other business areas. So this is our new building in the middle. I just arrow this is the School of Engineering building, but we moved out of that because of space. We have our own laboratory, quite a big. This is, I call, material bashing area, plus there are testing areas, modeling areas, and the student areas. And this is our group. You can see quite a few. About roughly we varied between 40 and 45 PhD students at a time. So now coming back to this actual lecture, objectives and contents. The primary objective of this lecture is to give an overview of polymeric composite materials. I wanted to qualify that because Purandar mentioned metals and alloys and other materials. So we are not going to talk about metal composites. I'm not going to go into ceramic composites. I am going to concentrate only on polymeric composite materials and their brief history and usual constituents. So why is composite materials that we have been doing it for a very long time, but the research started more in the last century, but middle of last century, sometime like that. Reinforcement of materials with rods, fibers, or particles. So rods could be, Purandar mentioned there that there's reinforcement in beams and everything. You have got rods. Fibers we use, glass fibers, very common, carbon fibers, or particles. Also now we go into nanoparticles as well. Now this is, if we look at, we used to have this for a very long time. We know that our tribal areas, they used to make bricks out of straws as well. Used to put straws just to hold the mud together. And we also see even in biblical time, they said that Israelis in Egypt added straw to the mud because it says that Exodus 5:7, you are no longer to supply the people with straw for making bricks. That clearly shows that the bricks had the straw, mainly fibers. They used to hold the mud, and mud used to protect the straws from the environment. It is still, that theory is valid, and we use for similar purposes the matrix material and the reinforcing material. Now, if we look at this kind of bow, about 1000 BC, that is also had to be cut in a particular area. We know the existence of long bows in India also for a very long time. But when they used to ride horses, these Mongols, they had to carry smaller bows, and which could be strung very quickly and had a very long throw. So these fibers, these wood, these strips had to be cut in a particular manner to increase that kind of throw, and you can say that you could create that kind of energy. So that was there. So where did it come from? Trees are the natural fiber composites consisting of cellulose microfibrils and encapsulated in a lignin matrix. So it has got cellulose, hemicellulose, and lignin as well. So this is the ideal example of natural composite. A tree is a wood, I should say, the classic example of composite material. Now, if we go back to history, we can see that evolution of materials, this is the rough kind of plot there, that polymers did exist very long time ago in the form of wood, skins, fibers, like that. Then composites were there in a tiny amount, straw, bricks, and then the paper also was discovered, and ceramics also went there with a stone, pottery, glass, cement, like that. Gradually that came to play some roles there in the materials area. Gradually, the metals had the more significant contribution until about 1960, 65, 70, like that. They dominated, and polymers were not that prominent, although at that time that a few, like 1900, bakelite was discovered, then nylon, polyethylene, polycarbonate, all these gradually, these polymers started taking over. And then, of course, we have now conducting polymers, high temperature polymers. And from there, we also started having composites. GFRP is glass fiber reinforced plastics, carbon fiber, or aramid fiber, that is also more advanced composites. With that, composites also, we have roughly these data for up to 2020. So I plotted there, and you can see the ceramics also went down a bit, and then again those materials have picked up in usage. So if we do this kind of thing, so polymers and composites and ceramics have started playing major roles, and metals also, they are fighting hard. In fact, if you have this very good top class alloying materials, aluminum, they are competing, because polymer composites took over in the aerospace aircraft industry, but metals also are fighting back very well, because glassy metals, aluminum, lithium alloys, all those things. So, but when we call composites, I would like to restrict it to like two different types of materials. Like phase, we will not call this as composite materials. Although in polymers, you can create completely different properties by changing the phase, and sometimes we have got now polymer composites. We have worked in that area also quite a bit. Now, current status, novel resins and high strength, high stiffness fibers, it has increased its applications and scope of applications as well. If we look at what is a composite material, briefly, if we go back, there will be a reinforcement, there will be an interface between the matrix and the reinforcement, and there will be the matrix. And so you can see the matrix is there, fiber and interface there. Now, primary role of matrix is to protect and hold the reinforcement material. And reinforcement, by its own name, you can see its primary aim is to reinforce and improve the mechanical properties. So and then there will be a small, very thin area, which is interface. Very important, because interfacial bonding between the matrix and the reinforcement has to be very good to improve the properties. And so interfacial shear stress is a critical parameter, and we try to improve the bonding by taking introducing various processes. So advantages why composite materials can not only two or more materials, and to really often produce superior properties compared to those of individual constituents. Individual constituents, most of the time, reinforcement fibers will have got very good properties, but some properties like toughness, they are often brittle. These kind of properties could be brought in by introducing proper matrix materials. So normally, what are the advantages? Because it is light, weight density of these composite materials is low, the specific properties are very good. High strength to weight ratio, high stiffness to weight ratio. So from that, it is essentially we are moving towards weight savings. So what we do is that because of that specific properties, we can create a much lighter material, or often they are called lighter products and with very good properties. And that's why it was picked up by the aerospace or aircraft industry. Now, another advantage is you often can make the actual product while preparing the material itself. Common engineering materials, you have the material and then you can extrude, you can forge, you can do something. But here often, like if you have thermoforming, you can form the material almost, you can lay the material, you can form it at the same time when the actual product is being manufactured. Also, integration of parts, good surface finish, less wastage, these are the advantages. Ability to tailor the material properties. Like we know the extruded rods have got some properties in the extrusion direction and different properties in the transverse direction. But when we use a metallic material, we really cannot control. Those properties are there, and most of the time we assume them as isotropic material. That means properties are the same in every direction. It is independent of the direction, isotropic. So that isotropy, sometimes you can waste the material. You have to put the material in the direction where you don't need that sort of reinforcement. So that is one advantage. We can put the fibers or the reinforcement in the suitable direction or preferred direction. That creates problems also. I'll come to that. The type of fiber and resin also, proportion we can vary, and we can change the properties and we create our own material. So that is actually, we can call it tailor-made material, and we can design that sort of material and produce them. Now, these are also have overall, the products have got good fatigue properties, thermal stability, acoustical insulation, and corrosion resistance. That is also very, very important. Now, there are some, you cannot get any free meal. So you have got problems there. It is high cost. Normally they are more expensive. Anisotropic behavior, because as I said, metallic materials, normally we assume isotropy. And here the materials, because we have preferred directions, properties are anisotropic. And anisotropy can create some problem in doing the analysis or very other, even design, they can create some problems. And then they can also have sensitivity to stress concentrations, humidity, because some of the fibers of some of the resin materials or matrix materials are affected by moisture. And test methods are not fully matured. They are not now getting more standardized, but still there are debates how to really, like the nano composites, how should we really check? How should we check the interfacial bonding property? Should we take a bead test? Should we take a crucible test? Various types. So there are some debates about the testing methods, particularly when we go for natural fibers. Natural fibers are normally grown, and it depends on country, season. Even from one fiber, properties can vary from top to bottom. So you need lots of tests, evaluations, and then take the average property. And designing is a huge problem. I was fortunate to chair a committee on the design with natural fibers, and for 2 years we argued and argued and argued. Eventually prepared. I don't think that was a solution, but at least we suggested a methodology. The applications, you mostly know that Boeing 777, these aircraft, there are so many parts which are manufactured out of composite materials, and there are some issues when you use thermoset. I'll come to that. Thermoset matrix material, their recyclability is a problem. So there are some criticisms on those things as well. So, and if you go to 380, unfortunately they'll be stopping. They won't manufacture it anymore. But the science has been sorted out. If you look at that, 60% by weight and 80% by volume were composite materials. The next generation 380, in fact, it was 65 to 70% by weight. So that will be utilized for the next generation of aircraft. Unfortunately, Airbus 380 will not be manufactured anymore because it was too big. It was difficult to handle. There are other applications: high-speed boat, high-speed ferry. These are some of these pictures. The hull picture we have taken for our America's Cup Challenge boat, and high-speed boats. We are doing some very good projects for U.S. Navy and U.S. Coast Guards. The high-speed boats, slamming. We have a slamming tank also, slamming load, and to design the panels depending on that slamming load and wind direction, all those things we can bring in. So you know the applications, the tennis rackets, pole vaults, means Sergio Bubka also broke about 17 times, I think, 17 world records. But if you look at his first record and the last record, maybe first one was with a bamboo pole and the last one with one of these composite poles. So of course, records will improve. Similarly, other things, teas and other things have been manufactured with composite materials. Cars, you know that very much. All the very expensive cars, they are going into composites, particularly electric car. Oh, we had a very good project for 5 years funded by BMW Munich on actually the manufacturing of the body. We had a good setup, very good. We did some very good projects. About 6 PhDs were supported by them, and all their electric cars had to be very light. Power generation application, buildings and structures, bridges, and also most recently you have very much gone into these medical applications of various part. From the human body can be replaced by polymers or polymer composites, and a lot of research is being done. We also have done quite a bit about the stent design and also the scaffold, tissue scaffold. Tissue scaffold, it was pretty successful, and we have been working with a company based in San Francisco. Okay, classifications. I'll go through these things very quickly. Fiber reinforced, laminated, particularly reinforced. I would like to mention one thing in this case. Sometimes people do a mistake. Always we specify a composite by the reinforcement first. We call glass epoxy composite, not epoxy glass. Fiber or reinforcement has to be mentioned, but that's a convention. Nothing wrong in mentioning glass, epoxy glass composite, but normally we mention like that: glass epoxy, carbon polypropylene composites, something like that. The matrix will be the second term. Also, we can have, based on reinforcement, we can classify natural, synthetic. Based on fiber length, we can have continuous fiber, long fiber, short fiber, and another thing is long discontinuous fibers. If we go into if I did have the time to go into the theory, every one of them has its merits. Continuous fiber will have the highest strength, manufacturing difficulty will be there, but you have the because of the large surface area bonded with the matrix material, continuous fiber is very good. But when short fiber is, actual processability improves, but the strength also decreases at the same time. So some people use long discontinuous fibers to have some kind of processability. At the same time, we can go very close to the properties of continuous fibers. So based on these things, we can classify composites. Also, we can have random, unidirectional, multidirectional, or woven material, fiber architecture, depending on that. Based on binders, we can have natural or synthetic binders. We can have natural material or synthetic materials. Based on binder types, polymers, metals, ceramics, and it actually reinforcement types, I should say, or binder, also polymer, metal, ceramic, also based on polymer types, thermoset or thermoplastic. I'm sure most of you are familiar, but very quickly, thermoplastics can be heated and deformed. Like if you take a milk bottle and heat it up, it will melt. But if you don't heat up in a temperature you can control, then it will be soft enough to bend or to reshape. Whereas thermoset, a classic example will be araldite. Once you set it, it is gone because you cannot deform it anymore. But thermoset materials have got better properties, normally mechanical properties, although they are brittle, but thermoplastic materials have got inferior material properties, but much easier to handle. They can be recycled, or they can be even and recycling is a very, very big aspect which is being considered now because of circular economy theory, that we have to go back. The products will have to be processed again or recycled, at least recycled, if not reprocessed completely. So if we have carbon aramid e-glass, I've given 3 synthetic fibers there, and these are all natural fibers after below that black borderline: flax, sisal, jute, rami, various things. Now, if we compare the specific properties, specific stiffness and specific strength, you can see that flax can compete with e-glass very, very easily. No problem there at all. The specific stiffness is very good. Pineapple fibers can compete. Sun hemp can compete as well. Some of them are not that good, but many of them can really compete with those synthetic fibers, particularly glass fibers. So people have gone into that. How can you? Because glass fibers recycling is a very big problem. Carbon fibers, now people have tried, but it is very expensive. Recycled products are not that good. So recycling is an issue, and that is why people are moving towards these natural fibers and also these thermoplastic materials or biodegradable polymer as well. That is quite expensive now, like PLA and others, but they are getting more use and the prices are coming down. Now, very quickly, manufacture of these fibers. I have used only one slide rather than this. Like wool can be replaced by like wood or jute fibers chopped, and then you can short fibers. You can prepare a mat, or you can mix it with dry mixing with the fiber, and then you can have a melt blending or compounding, and then you can, in fact, it's an extruder we have specially purchased for Milacron extruder for natural fiber extrusion. So we can extrude a section, or we can extrude a sheet of material 100 meters long, but about half a meter wide. So these processes are possible, and then you can use that sheet material or pre-preg that you have manufactured into molding process, and then from compression and extrusion, and we can check the properties, not flammability, but any other mechanical test samples to check the property. So essentially, these are the steps. Take the fibers, mix them, dry mixing, melt blending, compounding, then molding process, and then you can use this sheet material for thermoforming for products as well. Now, if you have continuous fibers, normally there are processes like solution processing, powder processing, commingling, melt impregnation. We were interested because solution processing, commingling, all of them have got some organic solvents involved, which are not very good, and people try to avoid. So we tried with powder processing, and we noticed that if you can control the parameters properly, then you can produce properties which are as good as those of solution processing. So we got that one. This is a PhD of Oliver McGregor, that we took various spindles of flax fibers with powder impregnation, just like our kite flying. Means really the idea came from there. Manja dear moto dhore, this powder, this is the powder impregnation. Powder is there, and it goes through. Instead of any solvent, we use water, and then water gets evaporated, but actually these powder thing, PLA powder, they get clung to this our this fiber as well. And then because it is multiple spindles are there, micro braiding, it can become a tape, a wide tape like that. And then you can stretch the tape, and that tape can be very long. It has got very good properties. And then we can use an automated computer controlled tape laying machine to manufacture products. So this, the student got some award and everything, and it was presented in New Zealand, also in California, to Germany, and German company was interested in manufacturing polyamide rather than PLA, and we did manufacture for them, and also they wanted to increase the width. So initially we used 15 spindles. I'm not showing there, but for that German company we set it up with 30 different spindles, and we could manufacture very good products, and they were very happy. Heater, you can see controlled heating was done. So property wise, you can see how good the properties could be. Flax PLA composite could consistently achieve 350 megapascal strength, much higher than mild steel strength wise, and 45 GPa stiffness. Of course, stiffness was not that high, I mean, not compared to steel, but strength wise, it was very good. When we use polyamide 12, then it was about 220 and 30. But that was the interest of the company, so we did, and we did work with them. Now, this kind of material, when you have got fibers introduced, normally in a sandwich panel, in a core material, the core does not have any reinforcement. So we thought that if we could reinforce them, if we could manufacture the core with some short fibers reinforcement, even with polymeric materials, we could get much higher impact energy, and it was a very attractive part. However, we did study the buckling, failure modes, everything, and then we published a paper also in Composites Part A. So this kind of product can take quite a bit of impact property. I'll come to that, why we were interested in that. Also, we took that if that is possible, can we use simply plywood? And this is, believe it or not, it is plywood passing through a roll forming machine. We could produce these plywood. Yes, that is the technique. You have to apply high temperature, and it has to be moist, has some moisture content, but very high temperature, you can destroy the wood cells in such a manner that they will not spring back. Normally spring back is a very big problem. Still there will be some spring back, but we can minimize the spring back, and we can also create a core material like that. So you can see the core material could be very thin, multi-layered, or you can have longitudinal core as well, like that. This is very easy one, and then you can bond them. We used ultrasonic bonding so that there was no material glue used there, and ultrasonic bonding, multiple head ultrasonic we used, And because the material was polypropylene, they bonded very nicely. And we did some peel-off test. So we were very happy with the bonding, and then we put the face sheets there and tested various properties without going too much into details. We did some optimization there, and we could produce very, very light. People often come and try to lift like that, but no, they're very light panels which could be used actually in the design room. People have got now specially designed room. Husband and wife can in fact literally change the wall. They are so light, and you can change the color throughout the year if necessary. So we interacted with the biggest building materials company here, Fletcher Challenge, and they were very interested. And then I'll say we moved into another area. That was our aim, because we started looking into flammability at the same time. This is the aircraft cabin class dividers. We sent one of these to Hamburg Air Show and it passed there. So we worked on this one. We worked with an aircraft interior manufacturing and design and manufacturing company. They are essentially based in Auckland, but also they have got branches in England and in the US. So it has been a very successful project. So I thought I would show this is the actual divider. When you go from the cattle class to business class or something, you have got these dividing boards. Apparently people get so frustrated they kick. That is why you can dent. That is why that impact property also was pretty important, whether you can create that kind of thing. Also, it had to have the fire resistance, which we achieved. From there, I am Purandar, how much time do I have?
Well, normally we say finish in an hour, 2 hours and 15 minutes. So
Oh no, I'll finish. We started late, so within an hour I'll finish, definitely.
Yeah.
No problem. Okay, thank you. So flammability is a wide topic. I would like to touch upon evaluation, because flammability, fire has become a very hot topic of research, really literally hot, because of the incidents that have happened in Melbourne, in Dubai, in England, all those tall buildings getting fire, loss of life, and also we get fire is a huge. If you talk to insurance companies, you realize how important that is and how many accidents or incidents we get throughout the year. So we started flammability evaluation, flame retardant development, and fire modeling. I'll touch upon these three and then I'll finish my lecture. So evaluation. Fire testing methods have got very specific methods we have to follow, standards we have to follow, and specifications are clearly given. So we know that this kind of fire is very, very difficult to control. But when you analyze, most of these fires started from the materials which were not structural, facade and things like that, or interior panels. People use very light materials there to make it attractive from outside, but their fire flammability testing was not properly done and they could catch fire very easily. So that kind of fire, now the codes are getting very stringent, that all these materials have to pass the fire test. The eventually problem is, even if the components individually pass these fire tests, combination or the whole structure may fail. That happens quite often because there is that scale effect is there, how big it is, how the fire can progress. I'll show you a couple of examples later on to make this point clearer. This is first we do on the material side, thermal analysis, TGA, and see that whether how it behaves against temperature. We also do some DSC test, then bench scale fire test, and I will spend a bit of time on this. Cone calorimeter is a scientific testing equipment, and burning test. This is accepted by the insurance companies, UL 94. It is for insurance companies, they need this burning test. And then also we can have some idea by having this limiting oxygen index, that the higher the oxygen index is, the better the flammability. And then this is OSU cone calorimeter. OSU is Ohio State University calorimeter. For some reason, aviation industry do not use they don't like cone calorimeter, stereotype cone calorimeter. Here the only difference is, I'll show you in a picture, the actual chamber is vertical. And why did they have to do that? Because it is less scientific than cone calorimeter, but you can only argue with them. They have their standard and they would like to follow that. Then we can have large scale tests, and our Building Research Association of New Zealand, they have got large test facility, a proper room. You put really the things on fire. And we have also interacted with NIST, National Institute of Standards Technology. They have a huge fire testing facility. We have interacted with them with the modeling, or we have sent materials and they have been tested in runs or NIST. So all these are standardized. You don't have to even look at these dimensions or anything. One is, this is UL 94, where exactly it says that how you should hold the material, how far, and what you should do. There is a cotton wool. You will have to see whether there is dripping or not. And depending on dripping or not, and when the fire starts, when the fire gets extinguished, we get rating V0, V1, or V2, or no rating at all. So this is the insurance UL 94 test. And limiting oxygen is a much more scientific test. And this is the type of test we do, vertical burn. I'll quickly do one thing, and because that video did not work there, if you look, we put the time, and you have to hold the burner for 10 seconds. If it gets extinguished within 10 seconds, you have to put it back. This is the standard. Please don't ask me why, but this is the standard. You have to go back and start reburning. If you look at polypropylene, it vanishes without any problem at all. But if we had APP, the fire retardant, ammonium polyphosphate, wool, then you retain parts of that. So you are not, some of them did get the V0 rating, others did not, failed completely. So this is the type of test we have to do to get, test. And then if we look at the cone calorimeter, it is that you have to hold the specimen, and then there is a heat source, heat flux will be controlled, and it will burn. And also the exhaust hood will analyze the gas so that we will know carbon monoxide, carbon dioxide, smoke production. Also, I will show you what is the main really output. Time to ignition, peak heat release rate, which is the most important, one of the most important outputs, total heat release, mass loss rate, smoke production, carbon monoxide, carbon dioxide yield. And we have our own cone calorimeter, various parts are there. There's no point in explaining them. But it is really a much more scientific experiment where we can control the test, we can analyze the exhaust, we can see whether it is carbon monoxide, because anything in the aviation industry or building industry, aviation industry now is you have to evacuate the whole aircraft within 120 to 180 seconds maximum. So preferably 120 seconds. Building, you have a few more minutes, but the gas production, as you know, most people die not because of the fire, but of inhaling those gases that either too much carbon dioxide or carbon monoxide. That's quite a dangerous output. So that is why we have to check. You can show that some composites, after a while, if it is too good, I'll say that later, because there's no point in telling that now. So we have got cone calorimeter, we have got exhaust gas, load cell, oxygen, and heat flux can vary from 0 to 75 kilowatt per meter square. And sample size is specified 100 by 100 and around 50 millimeter thickness, but or less than that. Actual exposed testing area is 88.4 centimeters square. They are very specific. If you don't follow that, they will not accept the result at all. So this kind of test we did, and then you get the output like that, heat release rate, peak heat release rate, and then how it gradually drops. Now you may drop by using some flame retardant. I'm coming to that. And what happens is that if you can form char, good polypropylene and wool, we form APP is an intumescent flame retardant. Like you remember that those snake fireworks that you use to burn, and it will gradually grow and like a foam. So it happens like that. It also, there is a foaming agent, and then it forms char. And because of the char, oxygen intake can get controlled and the fire can be put off. So this is a very important curve that we see how it goes. This is very important when it starts. This is just to show that there's smoke production as well. Now, challenges of various flame retardants. If we look, what is a flame retardant? So that flame can be controlled. This previously, until recently, or a couple of years ago, mostly people were using these kind of halogenated flame retardants, brominated. They were very effective, low cost, high performance, but their toxicity, because of high toxic output, they have been banned now. Means people are still have restricted usage, but most of the countries are banning them. So they have to be replaced. So they are replaced by like other things, or phosphorus based ones, high performance, high cost, and then there is a strength drop of the material. And metal hydroxide, you have to use in a large quantity, low performance, and strength drop. So we thought that there is a good scope of doing some research in this kind of area. So now let us look at the fiber fire situation. What happens? That heat flux is there, volatiles, combustion, and then it's possible feedback, heat release, smoke, other gases. Now, it starts burning. So if we can block this oxygen fire and possible feedback by doing something, that is why we are using, it is called intumescent, which is called char forming. It's a condensed char you form and the gas phase, and then you can block those inputs. They cannot go back and the fire gets extinguished. And that's how we get this char. And the quality of char is very important to control them. So intumescent fire, this is the thing, you can show the reaction. APP is very popular but expensive, ammonium polyphosphate. So we thought that whether we could replace ammonium polyphosphate. That was our aim, and I will say a few things and then finish. We looked at natural fibers, plant fibers, and animal fibers and mineral fibers. Now, plant fibers themselves are combustible. So people use that. You will never be successful if you have those plant fibers in the composite materials. But quite surprisingly, you see that actually peak heat release rate, rather than going up, it gets a drop. Total heat release, the area under the curve, more or less remains the same, but the peak heat release rate gets a drop. I think because of the fibers themselves are not conducting material, so the flux has to go around. I don't know, because I have not seen any analysis of that, but this is a conjecture. But we also wanted to have a look at silk, wool here, because wool, New Zealand produces a lot of wool, and they wanted us to look at the wool situation for composite materials from a fire side as well. So if you look at the two natural fibers, plant fiber has got lumen and then secondary wall, crystalline cellulose, primary wall, and amorphous lignin and hemicellulose outside. It is almost protecting the inside crystalline cellulosic fibers. Whereas if we look at wool fiber and other fibers, keratinous fibers are like that, you have got a lot of this keratin, which is a protein material. And whether protein is fire resistant. So we thought whether we can use that property to diminish the fire chances. When we used wool 30%, it dropped a bit, peak heat release rate, but it really was not that effective. So we mixed wool with APP, but APP percentage could be reduced very much, because APP is very expensive. So if we could reduce APP, it was an achievement. But we are not entirely happy because wool was not working. So we thought we should look at other keratinous fibers as well. And if you look at fibers, you can, whether you are going to use only the veins or feathers, or should we use the total. We thought for saving cost of manufacturing, we'll use the total feather. We actually chemically modified the entire feather. And what we did was, thanks to Daesung Jung, we calculated the cost of various keratinous fibers. We know that chicken feather, in fact, which is often a societal nuisance in many countries. In fact, we have put a price there, but sometimes you can get it free because they want to get rid of them. And so chicken feather, we thought whether we could work with them, because if we can use keratinous fiber, we add acid source, phosphoric acid we use very much, and blowing agent and char former. If we add together, then we notice that yes, the fibers get converted into very brittle fibers and coated. And what happened, in fact, then you can even pulverize it to get in powder form. So it is a non-toxic process, it is low cost and high performance. So we noticed that we started with wool with phosphoric acid. If we look at this, and I'm thankful to Daesung Jung because he understood chemistry much more than I did. So when we did with phosphoric acid and amine phosphate, we could actually penetrate, the phosphorus penetrated against the entire cross section. We were surprised ourselves. So when you do the analysis, carbon content and this has gone down, so we can do it improve that. And so I am not going to show it anymore, but we can see that using that modified wool, we could get or chicken feather, high percentage, we could get the V0 rating, and V0 rating. But otherwise, you get no rating at all. But these we could get V0 rating. And then flammability we can do. So also we did some cost analysis there to be competitive, because it was done by our business school. and because the students got that award, an international one for licensing, so we did some analysis. Wool was slightly expensive and electricity cost was high. That is why we moved from wool to chicken and chicken feather, and this is, we got some very good publicity there, that is why. But we did publish also in serious journals. So chicken feather, we used the entire thing and we mixed it just like we mixed other things, but we also got fire resistant fiber. We can keep it in fiber form. Also we pulverize deliberately so that we can mix very easily. And it was a sustainable product because the polypropylene is recyclable. FR, this chicken feather, is also, it's a societal waste nuisance, so it was very much appreciated. And when we use that, you can see that huge drop in there, that fire resistant chicken feather, and we succeeded in this intumescent fire. So again, the process upgrade was done and the costing was done. You can see now the chicken feather compared side by side. Electricity has come down to 7.5%, wool 12.5%, which is chicken feather is only 1.6%. And chemical, yes, it has increased, but these chemicals can be reused. That is, the other cost really did not change very much. So profit margin, of course, will increase, but chemicals can be reused. So we did publish in Chemical Engineering Journal very recently. So that is property. So we conclusions are that keratinous protein content fibers can be used. Similarly, we are using also milk casein now. Casein also has got this high protein content, and that can also be used as a fire resistant. So I will just have 2-3 more slides. These testings are fine, but you need, if we can model it, because then it can save a lot of time of this testing, and these pieces of equipment are not available everywhere. So we do a lot of testing for other parties as well. We get contracts from Australia on other countries. We have done it for Denmark, one group we are working with. So we do our modeling if possible, and so we started working with NIST because they have used that. I'll show you that numerical predictive model based on finite volume. They call Fire Dynamic Simulator, FDS. But we also embedded within FDS another package called PyroSim, and then we compared the strength properties by using typical abacus or anything like that, so that we can predict the properties after fire burning. So we have, and this is the thing I said, vertical. So vertical burning is done for aerospace. So we also analyze for horizontal, vertical, and also we published a paper where this can be at any angle, because fire will not follow this angle, 0 or 90. So at any angle, we try to predict what sort of fire performance or fire characteristics will be seen. So we predicted ignition time, ignition heat release rate, peak heat release rate, all those things. Acceptable, reasonable. It's not perfect, but we are still working on that. And because we can make it very close, but then you will have to, as you know, the fudge factor, all the input parameters you can play around with, but we want it to be as realistic as possible. So and then we applied that to a compartment where the fire will gradually develop and will attack the ceiling and other places. And also we are working now on the ducting. If you have ducts, how the fire will go. But this is the typical model you get after time. Fire starts burning, and then it hits the ceiling. If you have anything that damages, it burns for a while and then it gradually dies down. So it is the prediction model, and in fact in fire also they get very similar thing. And we were very pleased when we visited NIST. They had this picture also on their walls, and when my students showed our picture, they were also quite pleased. So it's a nice piece of work the student has done. He has gone back to Bangladesh now. He's working there. With that, I'd like to say these are our various publications, but thank you for your attention. Yes, I started at 12:20, 1:20, so 1 hour. That's fine. No, sorry, 2:20. Yes, I have finished now. Thank you. Hello? Hello?
Hello.
Yeah, I finished now. Thank you. Any
Okay.
question? Yeah.
No, first I would like to thank Devesh. Obviously, I don't need to re-emphasize the huge importance of the subject, and I can only say I wish our college, the college, had such special laboratories and projects facilities on things to come in future. One of the things Devesh must be knowing that when we talk of elevator ropes, wire ropes, 60% to 70% of the ropes has a sisal core for two
Yes.
reasons. Sisal core has a huge amount of lubrication retaining facility. Facility means capability, and the rope you are not allowed to lubricate from outside.
No.
Normally, a rod, when you put in alternate bending, you expect the rupture to initiate at the outer surface. Whereas because of stranding structure and friction between strands, you normally have failures where you don't see it from outside. So the sisal core with this source of lubricant has done wonder in the life of wire rope for the elevator application. I will request now, put the discussion open and request questions. I only hope that our students, both undergraduate and postgraduate and even PhD students attended, so that they can benefit out of this. Thank you very much. The discussion is now open to the participants.
Any question? Or I have explained everything so well, there is no question, or I explained so badly that there is no question. There could be two possibilities.
No.
Mr. Chairman, I must coax.
I'll take the first possibility. I'll take the first possibility. You explained it so well that actually I suggest the department to make it a point to go through this video in their class in the materials area, just of composite material. It's a wonderful presentation, starting from the basics and the way you advance. The first thing I want to make a quick comment on the line for the students particularly, because I'm a teacher also. The thing is that look at his logic, how he started. He started with Manjadava to then going for the phosphorus containing materials, then go to fibers, different types of fibers, etc. The key thing also is that he also looked at both experimental and simulation. One point I have to make sure this logical approach. First thing, he talked about different types of mechanism, how the fire spreads. And then he talked about intumescent technology, which is interesting. It's recently started working on. It's a very important thing. He also talked about this, how we are moving away from the fluorine content to phosphorus content material. Then he moved into the pulverization. That really raised my interest one way, that at the end of the day, this chemical reaction is a surface-dominated phenomena. So no wonder pulverization will do a better job, apart from mixing, etc. My comment or rather question to you is that, did you look into a little further down the road to go into the nanomaterials? Because we are talking about that, and well, I think,
Yes, we have done quite a bit of work with nano clay, especially nano clay, and more recently graphene. In fact, by one thing I did not say, because that we wanted to say good things about these intumescent fire retardants. Whenever you use them, I had one slide, you get a drop, about 20-25% drop in mechanical properties. You practically cannot avoid having that. So two ways we are trying now. We are trying to retain some fiber length so that we don't pulverize to this like particle where aspect ratio is almost 1. We are trying to keep some kind of aspect ratio, or and add 2 or 3%, 2%. If we add nanomaterials like graphene or nano clay, which is quite cheap these days. Graphene is also very cheap. From Alibaba, you can get graphene quite cheap. And so we can do that, and that way you can retain arrest the mechanical property drop as well. So nano clay or graphene also helps in the fire retardancy, but also that property drop can be arrested, because that is one bad aspect about all these fire retardants. They tend to drop the mechanical properties.
Purandar, I have only one comment to make. So my respect for composites has gone sky high after this lecture. I have seen composite research in Tokyo's National Aeronautical Laboratory, IIT Kanpur, IIT Delhi, IIT Bombay, IIT Kharagpur. I think my idea and my concept of research in composites have completely been transformed by Debes, though I am not a person from this area. Thank you, Debes. Thank you very much.
Thank you, Amitabh. If I could say something, I have said, volunteered to Sudeep, that I have got about 420 slides on composites, theory, lamina, theory of lamina, laminate theory, everything, and theory of continuous fibers, theory of short fibers. I give those, Amitabh, you might remember, or also SRM, I run a course for 7 days there, about 18 lectures. But I have volunteered. If necessary, it can be done remotely. I have just done twice for China and Korea. We can do it for BE College, but that will be much more, I should say that step-by-step calculation, theories, and theory of lamina, theory of laminates, and then how classical laminate theory, how to design. And another person would be very good would be Pankaj Da, Pankaj Mallik.
Pankaj Mallik to ete ache to, tomar oi Dearborn ache.
Dearborn. He has written fantastic books. I can show his book, which I follow. In fact, it is a gift. I would show that. It's almost doing...
Is our alumnus?
Yes, 66. 66 batch.
I met him at Dearborn, University of Michigan.
Pankaj the fantastic, in my opinion. Means we are nowhere near.
He came to our department also. He has given a lecture also. Pankaj became only.
Yes. He is a bit shy, but he's absolutely fantastic. In this area, he is superb.
He has also given a book to our library, or same book.
Okay. Yeah.
Uchida, any comment from you?
Yeah.
Yes.
Who's speaking, please?
হ্যাঁ এখনই ফোন করেছিলেন প্রফেসর পাঠক।
There are a couple of more comments in comment box, in the chat box.
Yeah. After Uchudha, can you kindly coordinate Vidyut, the question box and
Yes, sir, we can. Yes.
okay, thank you.
Yes. Yeah.
অশোক হাত চুলছে।
Professor Ghosh's voice is not audible. Professor Ochud Ghosh's voice.
Why
I will
Uchudha?
get the questions in the chat box. Almost Singh is asking about explosion fire. Which style is better modification?
Yes,
Is
sir.
it
Structure or placing multiple sheets like polycarbonate or metallic net in between the sheets?
quite a bit of reverberation? It is getting repeated twice. What was the question?
I should mute. You read the question chat box.
Okay, sir.
You
Sir,
read the chat box, you will get the question.
sir, can you hear my voice clearly?
There will be, noise.
Yeah, I can see all of you.
So can you hear my voice clearly? Then I can read it
Yes.
out for you.
Yes, no problem at all.
Okay, sir. Then I think we have got one question from a student, Amartu Singh. He is asking, for explosion fire, which style is better? Modification in seat structure, placing multiple seats like polycarbonate, or metallic net in between the seats?
For what? First sentence, for what?
For explosion fire.
Okay, so one thing I'll have to caution there, many people use film on the top and in between as well. But when you apply fire, what happens often, the thin film gets damaged first and then it attacks the core material. So we notice that unless you mix also with the matrix material some kind of fire retardant, this layered system may or may not work, because your one layer can get damaged by the fire, because you have got intense fire. Heat flux is going right on the surface and it damages the top surface and it goes into the matrix material and it affects them, and then the whole thing already has started burning. So you have to be very careful where you put those sheets and whether they are fire retardant or not.
Okay, I think, sir, the same student has got a follow-up question or comment.
Yep.
It's actually for RPG ballast along with bulletproof properties for bunkers.
Yes. Bulletproof properties, do they need actually fireproof? If they're bulletproof, they're happy, aren't they? Bulletproof properties are always with aramid fibers mostly, because of you get and they get absorbed a lot of energy. But I haven't seen recently any request actually from we have got with US Navy quite a few projects that we'll have to make them fireproof. Maybe it's a good idea. Yes, you can mix fireproof intumescent, or you can mix some APP with the material itself, matrix material, and use fiber as usual, aramid fibers.
But
Yeah. Only problem, if you mix this, sorry about that, Ashok, you're saying something. If you mix something, your viscosity goes higher, and then it is very difficult to penetrate. If you have any fabric material like aramid fabric, if you use RTM, resin transfer molding type process, or liquid composite molding, then it is very difficult to flow that, because viscosity is so high that it may not penetrate into those holes there in the fabric itself. So you have to be very careful. If it doesn't, then its other properties will go down. You may get fireproof, but other properties will be terrible. Yes, Ashok. Oh, Amitabh. Yes.
Who gets Ashok or Amitabh?
Yeah, I cannot hear any of you.
Can you hear me now?
Yes, I can.
No, I was going to say what you already answered, that to improve the fire resistant properties, you lose on the impact strength. So we have to judge which property is more important for a particular application. In the case of bulletproof, I think it is the impact strength which will be more important.
Yes, exactly. You have answered my that question. That your product is meant for specific end usage. If you identify my main usage will be to protect you from bullet, I think your other aspects, related areas will be less important. In the building materials, we cannot have fireproof material if it doesn't have the structural property, at least for the load bearing parts. If you have facade or anything or internal panels, we are working with a company, internal panels, you don't care much about the mechanical properties. Fire is the main thing. So yes, you are absolutely right, Ashok, that main thing, end usage will determine which property will be the most important property to look after.
Debes?
Yes.
Can you hear me now? I am speaking
very
slowly.
clear. Very clear.
So if you burn piece
Yes.
of wood, not burn, you heat it in an inert atmosphere so that only it gets carbonized.
Yes.
So can you use it as a reinforced material for making
it is, I could say that it is pretty hopeless because we are exactly, we have published a couple of papers. You form biochar, exactly as you said. If you, that is called biochar, you are absolutely right. In an inert, you can control the atmosphere, burn the wood, it becomes biochar. Depending on the temperature, your actual biochar particle can be very porous or surface area will be high. So we have a paper with a student who has gone to Sweden now, Oisik Das. Oisik is an expert in biochar area. Now, we did biochar, we tried to model as well. Really, the properties were not that good. Then also we looked at the flammability properties. On its own, biochar is not that good. So we are now trying to use biochar with graphene type carbonaceous other materials.
Polymer, if you do that polymer.
No, polymer plus some graphene or nano clay, because biochar, even in a particle, if you put in a polymer, its reinforcing properties are not that good, because interfacial bonding is not that good. That is the problem.
Very good, excellent talk, Deves. As I told, that my idea about composite
Excellent talk, but when you offer to give 480 slide lectures to BE College, choose your time. Don't do it at 2:30 in the night. You wanted to run a course for BE College students,
No,
as you said.
I thought I had to move a bit fast because I knew that I had too many slides, but I wanted to have an overall.
No, you are not getting my point. I'm saying you offered to teach a course for BE College students with your 480 slides. Those lectures must be held during your daytime.
Okay, you are in the audience. Okay, thank you.
Achyuta is having some difficulty in speaking, I think. His microphone is not properly working, I think.
You can send a chat message.
So there are a few more comments on the chat box, if I can read out for you.
Yeah, chat box, I can also read there. No.
Yes, please, you can also do it.
There are quite a few comments in the chat. The students have.
Yeah, in fact, we have a group here working on composites. They are primarily looking at, developing.
So somebody is working on OOF, object-oriented finite element method.
Yes, our
Yeah, I
Devas
can
is just
see that.
leading the team of students.
Yeah, yes,
I think
a student has written. I have
Professor
used your.
Doctor was also
Yes.
here, I think.
Oof. Is there any question? Is it coming?
No questions, more comments in general.
Okay.
Well,
Achyuta, do you have?
Achyuta, your system is now working? Microphone? I think he's writing something.
Writing something. Okay, it will appear.
Okay.
Yeah, chat is dark, so somebody is writing. Yes.
Yes.
Oh, thank you, Achyuta. I enjoyed the lecture. This encyclopedic. That is true. Encyclopedic. We bit too much.
Yeah, it's quite interesting. Right. So,
Hello.
if there are
I
no
have
more
got a quick comment for you. I think it may be a good idea in future for the future lectures to send them their whole presentation to you so that you can upload it in case some difficulty from the other side. Normally we do it in this type of Zoom presentation.
Yeah,
Have a one set with the lecturer who will be instructor, and also you have it so that you can communicate.
You are absolutely right. That is why I was contacting Vidut that whether I'll have to upload, and except the video, I could have used the Dropbox very easily. Some places I have not used any company name. Otherwise, they ask us to remove those names, but it was not a problem. I could have given this.
Okay, Debes, it is 2:30 a.m. for you, isn't it?
Yeah.
Exactly. I was going to say that
2:41.
unless you have got any burning question, unless you have got any burning question after
We should not give you
flammability,
more pain today. Yeah,
we
it's
might
too
say
late at night
goodbye
and
and
it's
good
too
night.
early in the morning. We should give some relief to Professor Bhattacharya. So let me take about a minute from the chair. So if the chair permits me just for Thanksgiving, on behalf of the department and on behalf of the yes. Let me proceed, please. So on behalf of the Department of Mechanical Engineering and on behalf of the Centenary Celebration Committee, let me thank Professor Debes Bhattacharya for this wonderful talk on composites, its development, particularly the aspects dealing with the developing fire resistant properties. It's a fascinating talk. I mean, we learned a lot. I believe our students have also learned. We also have a group working here. They are primarily focused on improving the properties required for, this defense applications. Maybe they can also, collaborate to have this work together so that we can also develop high resistance properties here. So I think Professor Devashish Datta will look into that if possible. And as Sir was saying, I will try to get his plan of lectures so that we can also plan it later in the department. So if we have students for this, we can run this short course sometime later. So I must thank our speakers, today's speakers, and I should also thank Dr. Purandar Bhattacharya for chairing the session, leading it with so sincerity and giving opportunity to our listeners here. So it's quite late for Professor Bhattacharya, Debes Bhattacharya. So we should all thank him, and let's try to close it here now. So thank you very much. Kamunda, thank you for joining. Professor Ghosh, I must thank you for remaining here all through, excepting one. Professor Mollik, I must also thank you for remaining present in almost all lectures. Right, so all seniors, I should thank you all. So with that, I would request Vidut to
Sir, I think the certificate of appreciation to
oh,
present.
yes. One last thing. I should request the chair to virtually hand over a certificate to our speaker. The hard copy of the certificate we should arrange to hand over to him or send through courier along with a token memento for this. So that we'll be doing later. If we have that snap of certificate, we can run it here. Do we have it now?
Yes, we have, I think. Sumana?
Oh,
yes.
I didn't expect that. That is something. Yeah. You can send me an
So
electronic
that's what
copy.
we can
That's not
give.
a
That's what
problem.
we can give.
Yes, sir.
And
I will email you.